just to remind ourselves, hopefully none of this is news to you, but also we could define the empirical standard deviation, which is almost but not quite, here we're dividing by n minus 1 instead of n, almost but not quite the average squared deviation of the observed data minus the mean. And there's this shortcut formula right there for this quantity. That's the empirical variance. N minus 1 dividing into that is the empirical variance. The empirical standard deviation is, of course, just the square root of the empirical variance, defined right there. And we divide by n minus 1 right here. We divide by the n minus 1 just to get a so-called unbiased estimate. What that means, let me just describe briefly what that means, is if we were to, under certain statistical sampling properties, if we were to get new data over and over and over again, the average of these guys would in fact actually equal the population variance that it was trying to estimate. That's why we divide by the n minus 1 for this property called unbiasedness. So anyway, the standard deviation is a measure of spread, whereas the mean was a measure of central tendency. And of course we divide by n minus 1 rather than n. That obviously doesn't change much. It's a factor of n minus 1 over n. If as n gets large, that doesn't make any difference, but it produces an unbiased estimate. Okay, so remember we had the process. If we took the data and subtracted off the mean, we got a zero mean process. If we take the data and we instead subtract off the mean, but then also divide by the empirical standard deviation, the resulting random variables, zi there, have both mean 0 and variance 1. So this is the process is called standard normalizing the data. And so it's centered at 0, and it no longer has units. Its units are expressed in standard deviations from the mean, right? So if something has a z value of 2, if zi equals 2, then that's going to imply that zi was 2 standard deviations from the empirical mean. It's often standardization is often very, very useful to get kind of unit-free quantities to compare across different measures. Okay, so there's normalization. Let's just briefly cover the empirical covariance. Okay, so the covariance between two random variables, and I write this in this class. I write covariance x comma y like that. What I mean is think of it. I think a lot of people taking this class probably have a computerish background. So think of this as, x is a vector and y is a vector, a list of numbers, and this covariance is a function. So this is a function that operates on these two vectors, and that's kind of what that notation means to me. I'm not defining it as the population covariance. This is an empirical quantity, but that's just a convenient way for me to write it, and you'll see how we use it frequently in the class. So the covariance is the sum of the products, the centered products, xi minus x bar, yi minus y bar. There's actually a shortcut formula right there. Again, just like the standard deviation, we divide by the n minus 1. So the correlation is related to the covariance in the sense that it's the covariance, which remember, notice the covariance, you're multiplying x's times y, so the units of the covariance are units of x times unit of y. If you want a unit-free measure, you would take this quantity, which has units of x times units of y, and then divide it by the product of the two standard deviations, standard deviation x and standard deviation of y. This has units of x, and that has units of y. And so the correlation is sort of a unit-free quantity. It varies between -1 and +1. A zero empirical correlation implies no linear relationship between the two variables. And this, of course, estimates a population quantity. If we have a sampling model, this estimates a population quantity, the population correlation. But for the time being, let's just think in terms of the sample correlation. Okay, so that's the sample covariance. We'll we'll use that. At any rate, here's some facts I already covered, discussed a little bit about the correlation. The correlation doesn't matter whether it's correlation x comma y or correlation y comma x, you get the same number. It's between -1 and +1. It equals 1 or -1 only if the observations fall in a perfect line or positively or negatively sloped